In this video, we want to discuss how to solve quadratic equations, at least basic quadratic equations, by factoring. The ACT will definitely test your knowledge of factoring, not just with quadratic equations, but with other expressions as well. At a basic level, factoring is a pretty simple concept. And most of the questions on the ACT that have you do factoring will test your knowledge of these basics. There are more strategies for factoring that we won't cover in this video that may be tested on. However, they are less likely to test you on more difficult factoring cases. All right, so let's review factoring. Factoring essentially is the distributive property in reverse. Let's take, for example, the number 10. If we break down the number 10 into its prime factors, which is something that you've probably done before or we've covered in other videos, you would get 2 times 5. And you can write that as 2 and then times 5, just like this. What you're essentially doing is you are undistributing the 2 and the 5 from 10. If you were to redistribute them, of course, you would just get 10. So that's essentially what factoring is. If we have another example with variables, we have x squared y. We can factor that into x times y, which looks a little silly because, well, that just equals x squared y. But again, that's the main idea. So now we're going to do some more examples of factoring with some different expressions. Let's take, for example, x squared plus 6x plus 3y plus 9. We don't actually need to find like terms or common factors for everything in this expression. We can actually group this up. In fact, there's something called factoring by grouping, which is actually useful in solving some more difficult quadratic equations, which we'll cover in another video. So let's factor x squared plus 6x. You may notice that they share an x in common. So we have x times x plus 6. Now we can factor the 3y plus 9. You may notice that they share a 3. So if we have a 3 and we pull that out, then we're left with y plus 3. And that is how you can factor that expression. Let's take the next example, 2x cubed minus 8x squared minus 10x. Well, you may notice immediately that 2, 8, and 10 all have a common factor of 2, and then x cubed, x squared, and x all share an x. So let's pull those out. That'll leave us with 2x times x squared minus 4x minus 5. We can factor x squared minus 4x minus 5 even further. I'm just going to do it for now, and I'll show you how it's done in the next section of this video. So what that simplifies to in factored form is x minus 5 times x plus 1. And of course, we can't forget to have the 2x out in front. If you want to check my work, you can always redistribute the x minus 5 times the x plus 1, and you would get x squared minus 5x plus x minus 5. And that would simplify to what we had above, x squared minus 4x minus 5. All right, let's get into factoring quadratics. Most quadratics you will be asked to factor have a quadratic coefficient of 1, meaning we have ax squared plus bx plus c equals 0, and the a is 1. That's what it means to have the quadratic coefficient being 1. So we can essentially pretend like it doesn't exist. So I rewrote it as just x squared plus bx plus c, instead of having the a in front of the x squared. When you factor a quadratic with the coefficient of 1, we want to get it down into factored form that takes the form of something like x plus a times x plus b. Let's actually distribute out x plus a times x plus b in order to figure out how to factor quadratics in this form. So that'll give us x squared plus a times x plus b times x. And if we factor out an x from a times x plus b times x, we actually get a plus b times x. And then we have the plus ab term at the end. Why is this helpful? Well, you may be able to notice that if we substitute for the capital B in the quadratic equation for a plus b, and we put in an a times b for capital C in the quadratic equation, that this will be fairly useful. And to show you concretely why, let's actually factor out a real quadratic equation or expression. So let's move on to the example, x squared plus 10x plus 25. Okay, so the 10 is what b is. So capital B is equal to 10. So let's substitute a plus b in there. So 10 is equal to a plus b. Now we have the 25 term, which is what c is. So c, being 25, is going to be equal to a times b. This should really allow us to figure out what a and b are. Can you think of a number a plus b that equals 10, and then numbers that, when multiplied together, equal 25? Well, what if we did x plus 5 times x plus 5? 5 plus 5 equals 10, and that same 5 times 5 equals 25. So that is the factored form of x squared plus 10x plus 25. Let's look at another expression, x squared minus 5x plus 4. So we know that negative 5 should equal a plus b, and then a times b should equal 4. This one may seem a little trickier if you're not used to factoring quadratics, because there's a negative. And we can't have two positive numbers that add up to a negative, so we have to include negative numbers. So, having said that, it might become pretty clear to you very, very soon that we can factor this if we simply take x minus 4 times x minus 1. To check your work, you can always redistribute. So we'd get x squared minus 4x minus x, which of course simplifies to minus 5x, and then negative 4 times negative 1 equals 4. So with those two examples, hopefully you can see that using that a plus b equals capital B and a times b equals capital C for the original quadratic equation should help you factor anything that is capable of being factored this way. Okay, let's move on to a unique situation called the difference of squares. So if you have a quadratic equation that is in the form of x squared minus a squared, you should immediately recognize that this could be factored very, very easily. So if we have something x squared minus a squared, the factored form is simply going to be x minus a times x plus a. Why is this important to know? Well, oftentimes the ACT will give you problems that look more complicated than they are. They'll just use a special form of something. If you know the special forms, you're going to save yourself a lot of time when trying to factor something. Okay, so let's do some examples of difference of squares factoring. We'll start out with x squared minus 4. So this is pretty basic. It looks like, well, we have an x squared, and then we have 4 can be rewritten, of course, as 2 squared. So this should just be x minus 2 times x plus 2. What about negative x squared plus 16? Well, that doesn't really look like x squared minus a squared, does it? Well, it is, but first we're going to have to factor out a negative 1. So let's factor out that negative. That's going to leave us with the term x squared minus 16. Now it looks like a difference of squares. So now we can factor out an x minus 4 times x plus 4, as long as we remember to keep that negative out in front, because we factored that out originally. What about 3x squared minus 243? Well, 3x squared isn't a square. Neither is 243. However, if we recognize that we can factor out a 3 first, we'll be left with x squared minus 81, which of course is a difference of squares. So now we can do 3 times x minus 9 times x plus 9. The next example also looks a little bit tricky. We have x to the 4th minus 16x squared. You may recognize that x to the 4th is just x squared squared, and 16x squared is just 4x, and then of course you square the entire term 4x. So we can actually write this as x squared minus 4x times x squared plus 4x. If you do it this way, however, you're not done. You can actually further this even more. You may realize that x squared and 4x, they share an x term in common. And then in the second part, the x squared plus 4x, they also share an x in common. So you can actually factor out an x from that first term and that second term. So what you're doing is you're actually pulling out x times x, or x squared, and that'll leave you with x minus 4 times x plus 4. The other way to do this problem would have been to recognize that x to the fourth and 16x squared shared x squared in common. So you actually could have pulled out an x squared as a very first step and then factored what was remaining. Either way would have resulted in you getting that final answer the same way. The next example, x squared plus 4, is a little bit tricky because you may take a look at that and be like, well, that's not a difference of squares. So you can't just say x minus 2, x plus 2, because that would mean that you get x squared minus 4, not x squared plus 4. So why is this included in this example? Well, you never know when the ACT is going to make use of imaginary numbers, or I. So if you rewrite this, you can rewrite x squared plus 4 as x squared minus 4i squared. And then you'll notice that x squared minus 4i squared is a difference of squares. And of course, if you remember from our video on imaginary numbers, I squared does equal negative 1. Negative 1 times negative 4 is, of course, positive 4. So this one's a little tricky, but if you wanted to factor x squared minus 4i squared, you would get x minus 2i times x plus 2i. Finally, we have x squared minus 7, which looks a little funny because 7, as we know, it's not a perfect square. So this is a difference of squares, however, if you simply recognize that you can use the square root of 7 times the square root of 7 is going to equal 7. So this actually ends up being pretty simple. It's x minus the square root of 7 times x plus the square root of 7.